folks, welcome to your first set of Chemistry 1 video notes for the calendar year. In our last unit, we discussed two very important types of bonds and how to predict the shape of covalent molecules based on their Lewis structures. In the first lesson of this unit, we'll be learning how to use that knowledge to compare the strength of attractive forces between different molecules and how those attractive forces affect the physical properties of the substance. More specifically, we'll be covering standards C.3.1 and C.3.5. There are two types of attractive forces in molecules: intramolecular and intermolecular. Intramolecular forces are the forces of attraction that occur between the atoms within a molecule. In other words, they're the bonds that hold the atoms in a molecule together. There are three types of intramolecular forces: metallic, ionic, and covalent. We've already learned about two of these three types of bonds. These intramolecular forces are significantly stronger than intermolecular forces. Intermolecular forces are the forces of attraction that occur between different molecules. In other words, these are the attractive forces that are responsible for molecules sticking together, as we see in a solid or a liquid. At the beginning of the year, when we talked about changing states of matter and having to add energy to a substance in order to overcome the forces of attraction between molecules, these are the forces of attraction that we were talking about. The three main types of intermolecular forces are London dispersion, dipole-dipole, and hydrogen bonding forces, and they're very weak compared to intramolecular forces. To help illustrate the difference in strength between intramolecular and intermolecular forces, think about a row of blue and pink rags that represent hydrogen and chlorine. One hydrogen is sewn to one chlorine. Then that pair, or molecule, is velcroed to another molecule that looks just like it. The thread that sews a blue and pink rag together is like the covalent bond between hydrogen and chlorine. And where one hydrogen chloride molecule is velcroed to another, those are like our intermolecular forces. If you were to pull at opposite ends of this line of rags, where do you think they'd break apart? At the velcro between each molecule, or at the threads that hold the atoms in each molecule together? Of course they'd break at the velcro. Our intramolecular thread, the bonds, are significantly stronger and require much more effort to break them apart than our intermolecular velcro, the London dispersion and dipole-dipole attractions in this example. Let's talk about the intramolecular forces first. Metallic bonding is the absolute strongest type of intramolecular force that we'll learn about. Metallic bonding is similar to covalent bonding in that we have shared electrons that hold the atoms together in some kind of structure. The difference is that these electrons form a mobile sea of electrons instead of being stuck between two atoms like in a covalent bond, or fully transferred between two atoms like in an ionic bond. They're free to move around as they please, increasing the amount of attractions that they can make between our fairly ordered positive nuclei. So the attractions that we see here are between the positive nuclei of the metal atoms and the moving or mobile sea of electrons. You'll find metallic bonding in pure elemental metals such as silver, gold, aluminum, and others, or in alloys or mixtures of metals such as brass, bronze, steel, etc. As you've learned before, ionic bonds occur when a metal donates an electron to a nonmetal. This creates a positively charged metal ion and a negatively charged nonmetal ion. This is the second strongest of the intramolecular forces. The attraction here is between the positive cations and negative anions. With their fully positive and negative charges, the electrostatic attraction between them is very large, making this the second strongest type of bonding. The larger the charges of our ions, or the smaller the radius of the ions, the stronger this attraction is. It's important to note that the ionic bonding between a metal and a nonmetal, like that of sodium and chlorine, is never just one positive metal ion and one negative metal ion. We tend to represent this bonding using just one ion of each because that's the simplest ratio in which they ionically bond. However, ionic substances exist in a lattice structure of multiple cations and anions all bonded together. You can see this lattice structure here. We still have a 1-to-1 ratio of sodium and chloride ions, but there are multiples of each, and they arrange themselves in a highly ordered lattice structure that gives it its three-dimensional crystalline shape. Covalent bonds are the weakest type of intermolecular forces. These occur when a pair of electrons is shared between two atoms. When atoms share electrons, each atom has a certain strength with which it can pull the shared electrons toward it. We refer to this strength as the electronegativity of that atom. When there's a difference in the electronegativity of the two atoms that are bonded together, those electrons get shared more toward the atom with the higher electronegativity. Having those negative electrons shared more to one atom makes that one atom electron-rich and gives it a slightly or partially negative charge. The other atom that doesn't have enough electrons is electron deficient and has a partially positive charge. These charges are similar to the charges we see in ionic bonding, but they're just fractions of whole charges. We denote them with this squiggly little S shape known as the lowercase Greek letter delta and a positive or negative sign. Like the north and south poles of the Earth or the positive and negative poles of a magnet, these different sides of the bond, positive and negative, are called poles. Since there are two poles, we call it a dipole and consider the bond to be polar. We represent the unequal sharing of the electrons by drawing an arrow parallel with the bond that points toward the partially negative or more electronegative atom. These arrows are called dipole moments. When the atoms have the same electronegativity, those electrons are shared equally between two atoms and no partial charges are created. The strength of a polar bond is slightly stronger than that of a nonpolar covalent bond, because a polar bond not only has the shared pair of electrons holding the two atoms together, but it also has some slight electrostatic attraction between the partially positive and partially negative atoms, just like we see in an ionic bond. Since a nonpolar bond does not have these additional charges that can add to the attraction between the atoms, they rely only on their shared pair of electrons to hold them together, this makes them slightly weaker than polar bonds. So of all of our types of bonding, metallic is the strongest, and then ionic is the next strongest, polar covalent is the next strongest, and then nonpolar covalent is the weakest. Hey, you've made it this far in the video, give yourself a short brain break by Googling a funny science joke and writing it in the very top left or top right corner of your notebook, depending on which page you're already on. Alright, let's get back to it and talk about intermolecular forces. London dispersion forces are the weakest type of intermolecular forces, but they occur between all molecules. Electrons are constantly in motion, and even though they may be shared equally between two atoms, since they're moving, they find themselves more on one side of the molecule than on the other occasionally. They don't stay in one spot for very long, but when they do end up more on one side of the molecule, they create a partially negative charge there and a partially positive charge on the other side of the molecule. This is just like we saw with our polar bonds before, but this time they're very temporary and very small charges that don't exist for very long at all. We still have a positive and negative side at that moment, and so we still have a dipole, but it's a temporary dipole, and that's what we call it. The fact that these dipoles are temporary is exactly why London dispersion forces are the weakest of all types of intermolecular forces. Since they're so weak, we tend to only really talk about them when we're comparing two molecules that only exhibit this type of intermolecular force. When comparing the strength of London dispersion forces, you only need to look at the number of electrons in the atoms or molecules. Generally, the more electrons there are, the more chances there will be temporarily unevenly distributed, and the greater the strength of the London dispersion forces. London dispersion forces explain why the nonpolar Cl2, with its 34 electrons, is a gas at room temperature, while the similar Br2 with 70 electrons is a liquid, and I2 with 106 electrons is a solid. It's important to remember that since all atoms and molecules have electrons, all atoms and molecules will exhibit some level of London dispersion forces. Next up are DipoleDipole forces. These are the forces of attraction between all polar molecules. The dipoles, partially positive and partially negative sides of the molecule, are permanent, unlike those in London dispersion forces. These permanent dipoles are caused by some atoms being better at holding the electrons closer to it than other atoms, aka having a higher electronegativity. Since these charges, or dipoles, are permanent, the attraction between them is much stronger than we saw with LDFs. By now, we should know that the opposite charges attract, just like in ionic bonding, or the additional attraction found in polar covalent bonding that we talked about before. In the same way, the partially negative atoms in one polar covalent molecule can find themselves attracted to other positive charges, like positive ions when we dissolve ionic compounds in water, or other polar molecules that have partially positive charges on them. In the same way, the partially positive end of our molecule will be attracted to any nearby negative charges in ions or partially negative charges in polar molecules. The more polar the molecules are, the larger their partial charges are. And as we talked about with ionic bonding, the larger those charges are, the stronger the attraction between them is. So to recap, all molecules experience London dispersion forces, and only polar molecules experience dipole-dipole forces. As a side note, if it helps you remember, we call them dipole-dipole forces because they're the attraction between a dipole and another dipole, or a polar molecule and another polar molecule. Lastly, we have hydrogen bonding. This isn't actually a type of bonding, hence why it's an intermolecular force and not an intramolecular force. But we call it hydrogen bonding because these forces of attraction are the strongest forces of attraction between molecules, and sometimes they can become close to the strength of an actual bond. However, generally, hydrogen bonding is still about 25 times weaker than a covalent bond. Hydrogen bonding is simply a special type of dipole-dipole force, in which the partially positive bit of each molecule is a hydrogen atom that is covalently bonded to a partially negative fluorine, oxygen, or nitrogen atom. Since fluorine, oxygen, and nitrogen are very small and very electronegative, there's a very large partial negative charge on them, giving hydrogen a very large partial positive charge. That partially positive hydrogen can then attract itself to the partially negative FO or N atoms of other molecules. That attraction is the hydrogen bonding that we're talking about. Since the covalent bond between hydrogen and FO or N creates the largest partial charges we can get with a covalent bond, these are a much stronger type of dipole-dipole force than any other, and they get their own special name. Again, these are just the same as dipole-dipole forces. They're just very special and very strong type of dipole-dipole force. So, the moment you've all been waiting for, how does this relate to the properties of a substance? Well, that's simple. The more highly attracted atoms, ions, or molecules are to each other, the more energy it takes to break them apart. This explains why it takes more energy, or a higher temperature, to melt steel, a metallic bonding substance, than it does plastic, a usually nonpolar covalent substance. It also explains why liquid substances with larger forces of attraction are less likely to evaporate than those with smaller forces of attraction. When those substances evaporate in a closed container, the number of gas particles in the container increases. As the number of gas particles increases, the pressure increases. At some point, it hits a happy point, or equilibrium, where the liquid is evaporating into a gas just as quickly as the gas is condensing back into a liquid. We measure the pressure at that point and call it the vapor pressure of the substance. Substances with more attractive forces stick together more and evaporate less. Therefore, they have a lower vapor pressure. So when we have more attractive forces, we'll have higher melting points, higher boiling points, and lower vapor pressures. Depending on the type of bond, the substance may be more or less likely to conduct electricity. In order to conduct electricity, negative charges have to be able to move around. Only substances that contain metallic bonding are conductive as a solid. Substances that are held together with ionic bonding must be dissolved in water or melted before they can conduct electricity. Covalent substances do not conduct electricity at all, even when they're melted or dissolved in water. To sum up some of the properties, metallic substances are very strongly held together, can easily change shape, have very high melting and boiling points, and conduct heat and electricity easily as solids. Ionic substances form crystals that are very hard and brittle. They have fairly high melting points and boiling points, but not usually quite as high as those of metallic substances. They can conduct electricity, but only if they're split up into their separate ions by being dissolved in water or by being melted. Finally, covalent substances have a variety of different physical properties. They have relatively low melting and boiling points compared to metallic or ionic substances, and even when they're dissolved in water or melted, they do not conduct electricity. In order to predict the relative properties of substances, we have to think about all of these types of forces together. First, think about what type of bonds the molecules have to hold their atoms together. This generally takes precedence, as intramolecular forces are significantly stronger than any intermolecular forces. As we mentioned before, if it's metallic or ionic bonding, they'll have very high melting points. And if it's covalent, it'll have a much lower melting point. If we're trying to compare two substances that both have ionic bonding, we use the size of their charges to compare their melting points. Generally, the larger the charges of the ions are, the stronger their attraction will be, and the higher the melting point will be. For covalent substances, since melting just involves breaking the molecules away from each other, not actually breaking the molecules apart, we have to look at the intermolecular forces. First, go ahead and figure out if any of the molecules you're looking at will have hydrogen bonding. If they have H attached to F, O, or N, they have hydrogen bonding. If one substance does and the other doesn't, the one substance with hydrogen bonding will most likely have a larger melting or boiling point. If they both have hydrogen bonding, compare them based on how many hydrogen bonding sites they have. If that's the same, then compare them based on how many electrons they have, because that means the one with more electrons will have stronger London dispersion forces. If neither of the substances have hydrogen bonding, compare them based on their polarities. Whichever is more polar will have stronger dipole-dipole forces, and will have the higher melting or boiling point. If they're both equally polar, or they're both nonpolar, then you need to compare them based on their London dispersion forces. To do this, compare how many total electrons each molecule has. The one with the more electrons, again, will have stronger LDFs. Our very last thing today is to figure out how to tell whether a molecule is polar or not. The first step is to determine whether the bonds in the molecule are polar. If they are polar, draw arrows or dipole moments along the bonds and point them toward the more electronegative atoms. This represents your bond dipole and should be relative in size to the difference in electronegativity between the two atoms. Second, determine the shape of your molecule. Lastly, make a good approximation as to whether your bond dipoles will cancel out or not. In order to cancel out, they must be pointing in opposite directions or be fitted into some kind of symmetrical shape that overall cancels out through vector addition. Generally, molecules that have the same outer atoms and are linear, trigonoplanar, tetrahedral, trigonal bipyramidal, or octahedral will be nonpolar because those shapes are symmetrical and the bond dipoles will all cancel out. Any molecules that don't have all of the same outer atoms, or molecules that take any of the other molecular shapes that I didn't previously mention, will likely not have all of their dipoles cancel out and will be polar. Knowing how to determine if a molecule is polar or not, based on its shape, is an incredibly important skill in being able to predict the relative properties of molecules. In short, in order to be polar, a molecule must both have polar bonds and be asymmetrical, or those bonds can't cancel out. Well, that's it for today, folks. I hope you were able to take away some information from this video. We'll do some labs and activities to help emphasize and practice these skills so you can master these two standards. As always, if you have any questions, ask.